Hi, we can start the class, I think so. Uh, so,
Yes, sir.
one second. Can you see the screen, Fahima? Hello.
Yes, sir.
Oh, fine. One second. Can you see the PPT now?
Yes.
Yeah. So, basically, this is the third week course, as you know it. And today, I will just go through the glances of last 2 weeks what we have discussed. I mean, last two classes, and also through the sir what he has discussed in the last 2 weeks classes. So basically, we started with the surroundings of the system, which is why we are doing the thermodynamics is to understand how the heat is transferred or work done by the system on the surroundings, or how the work is carried through the surroundings. And the system and surroundings are separated by the boundary, and we call it. And if you consider about the systems and the heat transfer between the systems and surroundings, there are three different types of systems. One is open, closed, and isolated. And how to describe the systems was, okay, we can describe the systems by saying the microscopic properties. What do you mean by microscopic properties means the microscopic properties we are not considering the internal, what do you say it, the rotational or translational energies of the particular molecules. So basically the microscopic properties are pressure, temperature, volume, number of molecules, density, and so on. By this we can describe the system. So once we have the system and which type of system, basically we have three different types of systems. So we will study morely about the closed system and open systems. And yeah, so basically this course is divided into two types. One is classical and statistical. Classical deals with the microscopic, and statistical deals with the microscopic, which we will discuss in the later part of the course. And you know that there are two different types of types, which is intensive and extensive. If I say the temperature and pressure, this can be the constant overall the equilibrium, and the extensive properties are the ones, internal energy, volume, and number of molecules. And there are three different there are total four laws which starts from 0 to 3. The zeroth law deals with the temperature, and the first law deals with the conservation of energy, and second law deals with the entropy mixing, and the third law deals with the entropy changes. So the further, if you see that, we have the statement saying that equilibrium. If I say that equilibrium, what do we say was, at microscopic level the system attains a state where it appears to be static and its microscopic properties remains constant and uniform. What does it mean was, if you are moving from one state to another state, say suppose if you are moving from temperature T1 to T2, and what we are saying was, the properties can be at an equilibrium if this is also equilibrium, this is also equilibrium. That's why it called as equilibrium when it is in the uniform path. So once we have, there are different types of systems, homogeneous and heterogeneous. As you all know that, homogeneous is the one system consists of a single uniform phase. Say suppose whether all the molecules are in either liquid phase or gaseous phase or solid phase. The best example is coffee in a thermoflask, where the different types of molecules are mixed together into a liquid form. And the heterogeneous is one system consists of two or more distinct phases. One is, you can say that, melting the ice or boiling water, or say suppose you have some other examples like mixture of, you can say that, human body, where we have the different parts with the different phases. And once we know the what is the different paths, we have the variables. What do you mean by state variables and path variables? Say suppose if I given the two distances from point A to point B, and if you are considering only the system properties at point A and then point B, and we distinguish that, okay, how much energy or how much is heat is required, or how much heat is necessary, then we call the state variables. Path variables means we will understand that how the molecule from A has been gone to B. So this is called the state variables and path variables. And basically in the later part we will focus more on the state functions, because we are not much widely focusing on the path variables, like we are focusing only on the entry point and exit point. So as zeroth law says that it deals with the temperature. Say suppose if you have two different places, and you are the third person, and you need to measure the temperature from the two places or the thermometer. It all starts from the thermodynamics first law, where the cold body takes the temperature from the hot body. So that's what I showed in the down example ABC. So further, as the initially the Kelvin Celsius scale has developed with two initials, two reference points. One is 0 degree Celsius, which is the melting point, and then he has taken the 100 degree Celsius, which is the boiling point, and he has done the experiments. So if you consider the expression for the ideal gas theorem, where PV and if we found out that the ideal one will be minus 273.16 degrees Celsius. So that's why we got the Kelvin scale, which says that T of K equal to T of D degrees plus 273 kelvins. So once we have the Kelvin scale with different temperatures, and then we have the ideal gas theorem, PV equal to RT, and the equation of state of if you have any what does this equation of state says is, if you have any two properties, intensive properties or extensive properties, you can find the third property by using these two properties. That's what equation of state. Basically, if you see any thermodynamics properties of the state or equation of the state means, see here you have the state. What is the state variable? As we discussed, the state variable, what does the state says was, it will focus only on the 2 points, either the starting point and the end point. It's not, it don't focus on the path where how you are going. So once this is there, we will focus on this van der Waals force on the later part of the class also. So general thermodynamics. So yeah, once we have the temperatures, say suppose we have the intensive properties of temperature, pressure and volume, and then we can distinguish the enthalpy and Helmholtz and Gibbs energy. So we have discussed some problems, and then we come to the first law. The zeroth law derives the temperature, and the first law discuss about the energy conservation, and we have seen that how work is related, and along with the pressure is related. You can see, you need to remember these two formulas. Sorry, at constant volume, heat transfer is dq equal to cv dt, and at constant pressure dq equal to cp dt. Okay, so then internal energy, we have u equal to q plus w, and the surroundings, you can see that w is not equal to 0, but the u total will be 0. W is not equal to 0. You need to remember this, because it is taken the different path. For if you take w1 which in and out, it will be in the different path, so it won't never be the 0. So you should remember this. Yeah, and this is a thermodynamic potential. So it is basically follows the Euler principle, where what we will do is, we will take any two properties and then we will use the chain rule, which is also called as Euler rule, and then we will do the analysis. And then we have for the closed system and open system. I have written a closed system and open system. So basically, in the following slides also, what we have done was for the closed system, we are assuming that we have taken the closed system with temperature and pressure and volume. So that's why we are in the last class or in the second week, whatever the sir has discussed, it has gone through the closed system and the Maxwell relation. Maxwell relation basically, I will explain you that in the later slide also. Yeah, so we have taken the properties of fluid. So you should remember that whenever we want to calculate how much, say suppose I have the boiling water. So where you can say that, okay, I have two phases, whether there is a temperature and liquid and vapor phase, but the system is only one. So it means water is converting to vapor. So if you use that formula, F equal to 2 minus 5 plus n, 2 minus the components are 2 minus 2 0, and the number of component is one, liquid, so one phase. So it means either you can change the temperature or you can change the pressure, and you can get the desired result at some time. At some point, say suppose if you take the triple point of water, where it is only one point. So if you take triple point where it is in the three conditions. So if you say if you take that triple point, one second, I'll just write it here. Yeah, if you take the triple point here, it will be F equal to 2 minus 3 plus 1, it will be 0. So what does it says was, you can't even change the temperature, pressure or volume. You can't even play with these things. So that's what this properties of fluids explain. So once you have discussed the properties of fluid, and we have discussed some problems which will be related to solve your week 2, and the end of the class we will discuss if you have any doubts regarding week 1 and week 2 problems. So this is the how they will calculate. I will explain you the same thing in the next upcoming slides also. So yeah, so until now we have discussed that, okay, how this is. So Maxwell relations. So we'll come back to the Maxwell relations. So why we are doing Maxwell relations was, say suppose I have two properties. Say suppose I have the temperature and pressure. Say suppose I have the temperature and pressure. They given that, okay, we know the temperature and pressure. Find the internal energy, or find the enthalpy. So to find out the any extensive properties with respect to that any two given variables, we need the Maxwell relations. That's where the Maxwell relation comes. So basically, this is the mnemonic diagram. If you see, this is the, I think I can write, one second. Yeah, if you see, so bear with me for today's class. Yeah, if you see, this is the mnemonic diagram. What does this mnemonic diagram says was, you can remember like this: A, G, in alphabetic order, A, G, H, U. You know the formula for U, right? Already, you just remember the formula for U. You can remember every other things. So it is U equal to TdS minus PdV, and just draw the lines like this. Okay, So now we have, so if it is the arrow is showing towards it, it will be negative. If the arrow is away from it, it will be positive. So if you remember this, so now if I write it formula for the dh, it will be dh equal to, see if it is dh, so the two sides the arrows are not towards it, so the arrows are away from it, so it will be positive from both sides. So it will be positive and positive, and this will be the variable for this. Okay, these two are the variables for this, so it will be ds and it will be dt, and the opponent will be the same thing. So p, sorry, it will be t, right? It is t, it is p, so it will be p v d. Is it clear this, how to find it from the mnemonic diagram? So you can do the same thing for the delta g, delta a, delta u, and delta h also. So basically the mnemonic diagram helps us, the basically the mnemonic diagram which will help us to understand the, okay, how to give the formulas for the certain component which we discussed in the later class. So as in that, in the third week also we have discussed this one, h of t comma p and s of t. So suppose here you know that h is, we can write h as a function. Here we can, sorry, you know, here you can write h as a function of s comma p. But say suppose in the given questions or somewhere we know that we can find out, they will ask to find out the h in the presence of t comma p, or s in the presence of t comma p. So here you can see that h is the variables of sorry, pressure and the entropy, but they asked to find out the h value of enthalpy with respect to the t and p. So the best way which we have done in the last classes also, if you see, we know that h equal to u plus pv. I think you have it in the third week assignment problems also. It will be better to understand this. H equal to u plus pv. I did the differentiation. Dh equal to du plus dpv. For this component, I have applied the chain rule. Dh equal to du plus pdv plus vdp. So as I know that dh, again the q, u is equal to q minus w. If I do, sorry, if I use w as PV and dW as differentiation of PV. So this one will get cancelled. So then we have dH equal to dQ. So we know that from the work problem, dQ by dt equal to, at constant pressure, is equal to Cp. So that's what gives us dH by dt equal to constant pressure. So we got dH by dt, we got dH by dt, and then if you see, we also know, so this is the first formula which we know. The second formula which we know was dH equal to Tds plus Vdp, and we have applied the partial derivation with respect to the constants, and we got this equation. One second. Yeah. This is somewhat confusing. So we got the second equation here. Here we got the second equation. So from this equation we can write the Cp. So we know the from this value from here. So Cp by T equal to ds by dTp. So we got the ds also. So here basically they ask for this one, h of, sorry, h of t comma p, h of t comma p, s of t comma p. We got h with respect to the t at constant pressure and s with respect to the t at constant pressure. So then we also know that h is a function of entropy and pressure. So if you apply the Euler's formula and Gibbs Duhem equation, so we will get this one. What I have done was, once I get this one, so I need to know h p with respect to the constant temperature. So I have applied that thing. So here if you do it, so here also you will get, so here you will get dp by dp at constant temperature because of this. So I cancelled it. So that's why you have this equation. So from Gibbs energy we have all these formulas, so which you get at the finally. So this is the formula, and the ds by dt also same thing. So ds by dt at p you will get it from here, and ds by dpp you will get it from here. So this is again the compressibility factor. If you know the compressibility factor, we know that expansion and compressibility factor. Expansion formula we know that alpha equal to 1 by v dv by dt at constant pressure, beta equal to minus 1 by v, it is compression, minus 1 by v dv by dp at constant temperature. So then we have the two formulas. So this is the, sorry, so these are the two formulas which you will use, you can use it to find the system problems. So do you have any doubts in this, how to find the entropy? Say suppose as the h as given as s comma p, we know this one, but if the question is described to find the h of t comma p, so this is one of the way to find out. So is there any doubts on for this also in this slide, how to obtain any one of this value, or if you want me to explain again, I will explain it. Okay, I think there are no doubts. So further I will go. So there is another way of solving the same thing. So here what we have done was, we have taken h equal to u plus pv, h equal to u plus pv, and dh equal to ds plus vdp, and then the Gibbs energy. So the another way is, I have h of t comma p. What I will write it in the Euler form. So this is the first thing you should do, and then I know that dh equal to tds plus vdp from the mnemonic diagram. So thus I written here dh as here and dh is also here, if you see it. So now I have this one. So now I will write at constant pressure. So because see, this is the see, whenever I say that this is the constant pressure, right? Okay. If it is constant pressure, the VDP will be 0. So this will be 0. So then it will be dH equal to TdS by dPt at constant pressure plus dt. So here it is not the constant pressure, that's why we are not keeping it as 0. So dP. So then, so one second. So then we know that dH equal to TdS plus VdP, which we have written same thing here. So now if you apply the formulas, like if you remember in the second class we have discussed about the reciprocation formula, which I think I already shared with you. The reciprocation formulas, if you need, you can look back into that videos. So from there you will get the dH with the dTp. So how you got these formulas, you will get from the reciprocation problems which we have, and you know the Gibbs energies also. So these both, so basically if you remember the reciprocation formulas, how to calculate this reciprocation, this two are comes from the reciprocation and legendary for transform, which we discussed in the second week class. So then we will apply this both here. So here if you see dH equal to, I written this as it is. So now this so there are numerator 2, so I separated both the numerators, and here you will get, see, dc by dtpp, which is nothing but the, here if you see, if I can write like this also, this one. So alpha equal to 1 by v d, sorry, so alpha equal to 1 by v dv by dt at constant pressure. So then dv by dt at constant pressure equal to minus alpha v. So that's what we have written it here. If you see it here, we already have the t form t1. I kept the t as it is, and ds by dp at t is equal to minus dv by dt. Dv by dt equal to minus alpha v plus v. So dp get cancelled here. So we got v dp. So then I take the common. So this is another, sorry. So this is another way of solving the equation. And then we have, yeah. So is there any doubts regarding this way, how to calculate this way? This is the, basically it follows the Jacobian method. Instead of showing the Jacobian method, I directly done it. If there are any doubts regarding this, I will explain it again. If there are no doubts, then I will go further. So once we know that, so we can, okay, so this is like one example for you. If you want to try, you can try it, how to calculate for u of t comma v. So in the second method, so initially, say, suppose if you see, what I want to show here was, see, suppose u is a function of, here also u is again function of s comma v. Okay, but the question here I am asking you to do for u of t comma v. Okay, so because we p comma v comma t are the three properties which we can play with. So from these three properties, suppose if I given that, okay, find the u with respect to t comma v, we know that, and we know that u is a function of s comma v. So how to go from here to here? So by using the second method, how I said, so you can take, you can apply the Euler's formula, du by dt at the constant v dt plus du by dv at constant PV, and we also know that u equal to TdS minus PdV. So I apply it here, and then at constant volume, because here we are applying at the constant volume, dv will be 0, so this will get cancelled. So then du equal to TdS by dt v and dt plus, so this I have written as it is. Sorry, uh, if you take the from Helmholtz energy, the same thing, if you apply the reciprocation formula on Helmholtz free energy, you will get this formula where it says that ds by dt equal to dp by dt. So that's what I have written here. If you see t dp by dtp minus, so I cancelled out this thing and you get minus dv. So here you know alpha equal to 1 by v as we discussed just now, beta, sorry, k equal to, so some papers they will write alpha and somebody will write beta, so both are same. So now if I take alpha by k, it will be dp by dt. So that's what the dp by dt is become to alpha by k. So and this is the formula. So if anybody asks you to find out change in the internal energy with respect to change in the internal energy with respect to t comma v, so this is the another way you can find out. So for this, the first method we need to remember everything, like okay, how to go from here to here. For this you need to remember only the reciprocation formulas and the legendary transforms. If you remember these two, it will be easy to help to solve the problems. So once we have done with the, I think this is clear for your side. If you have any doubts, you can ask regarding this. I will explain it again. Is it clear, this one? I think there are no doubts regarding this. So then, if there are no doubts, so can you hear me? Hello, if somebody can tell me that. Hello. I think, am I audible? Hello, Fahima. Oh shit.
Yes, sir.
Did the call got cancelled?
Yes, sir.
So okay. One second. Okay, one second. I will start the class. Hello.
Yes, sir.
Yeah. Okay. Fine. One second. You can see the screen.
Yes, sir.
Yeah. Okay. Fine. I think it's one second. Then I need to do this. Mm. So where is that true genius? Okay. Fine. So basically, homogeneous heterogeneous. Hmm. The screen is visible, right?
Yes, sir. It's visible.
Okay, fine. Thank you. So, so we have different types of homogeneous systems. So one is, yeah, we have different types of homogeneous system and heterogeneous systems. So as we know that because we can say the coffee in thermos is one of the example, and then heterogeneous system, a glass of water and ice. So then we have the state variables and path variables. In the state variables, what is the common was in the state variables we are focusing on only the starting point and end point. Say suppose I am moving from point A to point B, I will focus morely on the I will focus morely on the point A. What is the values at point A, thermodynamic properties, and what is the values at point B. So I will take the values of these two, and then I will calculate it. If I am going through the path variables, what I will do was, okay, I will take, okay, how I went from path A to B, whether I followed isothermal process, adiabatic process, which process I have followed. Uh, See, suppose if I take, I will explain that in the further video also. One second. Yeah. So in the zeroth law, we know that we'll come to the zeroth law and then first law. So zeroth law, as we all know, that it deals with the temperature, and if you are the one who is calculating the temperature between two different places, We can either do it by using the mercury or the manometer or the color change in the material. And as we all know, the temperature goes from the warm body, cold body to, sorry, hot body to cold body. So that's what we explained in the down case. So once we know the zeroth law, and which was developed by the Celsius, using zeroth law, Celsius defined the scale, which says that he has taken the points. One as regarding to the, with respect to the water, one is 0 and one is another is 100 degrees Celsius. So what we have done was, what we are doing it here was, and then using the ideal what Kelvin was done was, if you have any function, it won't all the functions will not satisfy the Celsius scale. So that's why he given the new Kelvin scale, which we are studying now. T of k equal to t degree Celsius plus 273.15 Kelvin. So I think this is all we have discussed in the last class. So Van der Waal I will explain it later in the last part of the class. So now we will go to the class. So yeah, so we have the thermodynamic properties, and you know that we are applying the chain rule here. Using the chain rule, we can apply. One second, yeah. So using the chain rule says, chain rule is nothing but a Euler rule. If you say any rule, what it says was, we can do, suppose if you take the p of t comma v, it will give dp equal to dp by dv. You can understand this. So by applying the chain rule, we can get all the properties which we said in the last class also. And then if we have the for closed system, open systems, we have the formulas. So until last class we have discussed this, so Maxwell relation and all the things. So I will explain you again how to do enthalpy and entropy calculations. I think this will not go now. I thought due to bad. Okay, fine, no issues. So you can see the screen right now. I think it's fine. Hello.
Yes, sir. Yes, sir.
Okay,
Yes, sir.
okay, it's fine. Thank you. So Maxwell relationship. Why we are doing the Maxwell relationship was, say suppose we have given the properties of any system. Say suppose I have the system with temperature and pressure, but I need to find out. Okay, say suppose I have done some experiment and I have taken the values with t comma p. I have taken temperature and I have taken the pressure. So now I want to calculate what is the changes in the internal energy, what will be the changes in the enthalpy, what will be the changes in the entropy. So for this, but we know that u is a function of, say suppose if you see it here, u is a function of s comma v. Here if you say h is a function of s comma p. But I have done the experiment on t comma p. Say suppose I have done the experiment on t comma p. So now, okay, it's better to explain the new slide. One second. I will explain it here. So you can see the screen right now, the plain screen.
Yes, sir.
Yeah. So you know that u is a function. Sorry, what something is happening. U is a function of TdS minus PdV. So you know that u is a function of s comma v, as well as you know that h equal to TdS plus VdP. I think so. Here h is a function of s comma p. But say suppose you have carried out the experiment. You have carried out the experiment with the values of temperature comma p. So now how will you find out the h values and u values? So this when the Maxwell has generated the relations for all the extensive properties which we need to find out for all the thermodynamic properties of the state. So that he generated by using, he has taken the Gibbs energy Ag Hu. He has taken through alphabetical order. So you know that u is a function of, and he has done the two arrows. And you know that s is a function of v, yes, and it is a function of p. You know, if you know only two formulas, suppose if you know only, you can say that, sir, I know only formula for u equal to TdS minus PdV. I know this formula, and h equal to TdS plus VdP. I know this formula. If you say about these two, we can generate all the other two. Say suppose you have taken AgHu, and if the arrow is above, if the arrow is outside the thing, it will go as positive. If the arrow is towards it, it will go as negative. Say suppose if you take H here, the arrows are opposite way, so it will be positive, positive. And these are the two variables which you are focusing, so it will be ds, dp, and S is going through T, and this is going through V. So now you can write H equal to TdS plus VdP. Say suppose if I go for U in one case it is going outside from it and one is coming through it, so one will be negative, one will be positive, one will be negative. The positive one is S, so here it will be TdS because T is outside, ds is towards it, and here it is dV and P. If I take the Gibbs energy, so here both the arrows are towards it, so it will be negative and negative. So if I say and the negatives will be of dV, dt, and the V is converted from P minus S. So this is the formula for U. And if I take the G, so one is positive and one is negative, because you can see the one is coming towards it, the negative one. So this will go negative, so it will go as these two are the variables, dt and dp, and P we have minus V dP, and for G we have S dt. So this is the formulas. This is how we can get the formulas. From here you can apply the reciprocation formula which we discussed in the last class, reciprocation and Legendre transform. So it is better if you have any exam or anywhere in the initial class itself, it is better to write it down, okay, these formulas, and in the one side, like side of the book, you can write, okay, A, G, H, U, this is going this way, and this will be the formulas for U, H, G, A. And then if I apply reciprocation problem, what will be the formulas, and then transformation formulas. So it will give a better way. I will explain you that in the later way why it will be better way. So if you see, we got this one. If you see, we got dH equal to dg. Change in the dg is sdt minus vdp. So if you see, yeah, that's what we got it. I think, yeah. So any doubts in this?
No, sir.
Okay, fine, thank you. And then, okay, now in the last class also we have discussed this one, h of t. So suppose we all know that h is a function of t comma s. Sorry, p comma s, right? H is a function of, yeah, h is a function of p comma s. H is a function of p comma s, but they're asked if I did the experiment with the h t comma p, how to calculate it. There are two ways to calculate. I will show you the first way, which the previously it was done. So I think you can see the screen here. H equal to u plus pv. We have taken h equal to u plus pv and we have applied the differentiation. Dh equal to du plus differentiation of pv. From here what I have done was I have applied the chain rule to this one, to this component. So I applied chain rule to this component. So what I got was dh equal to du plus pdv plus vdp, and we all know that u equal to q minus w for the closed system. We are talking about the closed system. So closed system, dq equal to dq minus dw. So then again w equal to pv. So these two will get cancelled out from the w. Then you will get the dh equal to dq. So once you got dh equal to dq, so we know that from the work dq equal to cp by dt. Sorry, dq by dt equal to, at constant pressure, is equal to cp. So that's what we are written it here. So now it is dh equal to dq. So it will be dh by dt equal to dq by dt at a constant pressure. At a constant pressure, it is equal to cp. So that's what we have written it here. And then once you have this formula, so we also know that dh equal to tds plus vdp. So I applied the reciprocation formula here. So I got dhp equal to dt by. So here you can use this one here, and you will get ds by dt with respect to cp by t. So here now what you got was, so so we know that h is a function of temperature. So which means you need to get dh by dt at constant pressure, comma, you need to get dh by dp at constant temperature. And if I talking about s of t comma p, you need to get ds by dt at constant pressure and ds by dp at constant temperature. So now you got the this one. So dH by dt you got this one, and ds by dt you got this one. So for this one, we need to use the third one which we know. So now you have taken the three ways. First way is basic one, h equal to u plus v. Then you have taken, so if you see we are going in the three different formats. The first one is in the reciprocation formula. If you see the table, this is basically f minus ax, if you have seen it. Then we have applied the updated version of this. Then the third point. So this is how you should go. So we have h of s comma p. So then we are applying the Euler's formula. So from Gibbs energy, we know that if you apply to the Gibbs energy reciprocation formula, we will get ds by dp at the rate equal to minus this one. So this is nothing but the expansion formula. So what does the expansion says was 1 by v equal to change in the volume with respect. So suppose we have the one system where the volume is increasing when we are heating it from the down at constant temperature, will give the expansion of the system. So that's what we have mentioning it here. So if you see so we have the dH equal to this one, but we don't have the this value, this one. So what we have done was I have divided it by partial derivation with the pressure at constant temperature. So I will have this value, and we know this from here uh, it is minus alpha v, and dH by dp we also know that dH by vt equal to this one. So then we have the this formula. So if you have any doubts regarding this, so you can see dH by dp at constant pressure is v. So I applied v here. So what you will get was, here it is plus v, here you will get minus alpha tv, because dH by ds is t, you can see it here. And so here what I have taken was v as common, and 1 minus alpha t, that's what we have written it here. So then we have the entropy, as we already know the ds by dt value, and ds by dp by dt we will get it from Gibbs energy. So that's why it is directly get it. So any doubts in this calculation of what do you call enthalpy and entropy with respect to time and temperature and pressure?
No, sir, no doubts.
Okay, if there are no doubts, and then we will go. And this is the second way. So this is the easiest way which I found out. So what we have done, what we are doing was, we'll apply. Say suppose in the same, I want to show the different method. We have taken h of t comma p. So dH equal to dH by dt at constant pressure dt, and this is the best one which we know. What I have taken was, we know that h equal to tds plus vdp. So I applied it here, and what I have done was at constant pressure, because we are using at constant pressure and constant temperature. At constant pressure, obviously this will be get 0. So that's what we get it 0, and then dH equal to T ds by dp p dp plus this one. If there are no doubts regarding until this, then we will go like, we know dH equal to TDS plus VDP. I applied the reciprocation formula. So now I know this Cp by T equal to ds by dTp. So which we will use it, see here, ds by dt equal to, okay, I'll show it here. And from the Gibbs energy we already know this formula. So if I apply it here, the same thing, dH equal to TDS by dt, dt at constant pressure dt plus there are two numerators. So what I will do was, I will shift the two numerators as a single entity. So now I got these two entities. So at dp, so this will get cancelled, and we will get the vdp. So this is fixed. And here dc by dt at constant pressure is cp by t. So t cp by t minus, so this value we have already t. So the ds by dt from Gibbs energy, we will have this one. So minus alpha t, and this one. So this way it is equal to dH equal to cp dt plus v into 1 minus alpha t dp. So this is another way of doing it. So this is basically done from the Jacobian method. Without explaining the Jacobian method, I directly shown how we can do it. And this is second one, which is not explained. I just want to give as an example. You can try it out this example, where we have, say suppose we all know that u is the function of TDS minus PdV. So it means u is a function of s comma v. But you have done the experiment with the temperature and pressure. You want to find the internal energy. So now what you will do was, you will apply the Euler relation. You will get du by dt at you have done the experiment at volume, T and volume. You have the temperature. Say suppose I have said that the temperature is raised from 100 degrees to 200 degrees, and the volume has decreased from this point to this point. So then I asked you to calculate the internal energy, and I have given the specific heat values. So then how you can calculate was, du equal to du by dt Euler application, and you know that I have done through the second equation, second format, which I have shown the Jacobian method. U equal to T ds minus P dv, and du equal to T ds minus P dv dt, and I have just uploaded it. And as you say that it is at constant volume, what we will get was dv get cancel, sorry, it will come 0, and that's what we written here, du equal to T ds by dt v dt plus this one. And from the Helmholtz energy we will get ds by dv at constant pressure equal to dp by dt. So that's what so now I moved it here, so dv get cancelled, you will get minus t p dv, because there is no temperature constant, there is no temperature system, so that's why we are removing this. And we have T ds by dt, and you know that you know this one, ds by dt at constant pressure equal to Cp by T. Same thing, ds by dt at constant volume equal to Cv by T. So that thing I applied here. Here the Tt will get cancelled, and ds by dv will get it from the Helmholtz energy, dp by dt at constant volume, and you know that alpha by, sorry, yeah, and you know that alpha by k equal to dv by dt. What we have done was we are taking the expansion divided by compression, so expansion is nothing but 1 by v dv by dt at constant pressure, and the compression is minus 1 by v dv by dt at constant temperature. So we are applying expansion divided by compression to get dv by dt. So this will go up, so it's basically it will be like this one. So we will get dp by dt, so that's what dp by dt, so it is nothing but alpha by k. So that's what I have written here. So we have t already, so this is the final expression. So the final expression I will write it here again, du equal to t Cv by T dt plus T alpha by K dp, sorry, dp will get cancelled because at constant pressure, because we are focusing on this, minus P dv. So this is the formula which we can do it, because here you can see, here you got, if I say here, if I show it again, 1 second, I will write it again. So it is grammatical I think it is a mistake from the PPT side. So you are doing the expansion by compression, it will be dv by dt divided by dt by dp, it will go as dv by dt into dp by dv, so it will come as dp by dt at dv. So that's what we, this dp will go as dv, so now we will take dv as common, so it will come as t alpha by k minus p dv. So that's why the final equation will be du equal to Cv dt plus T alpha by K minus P, so dV. So this is the way we can calculate any given the term. So say suppose we have shown two different types. If I given the H in the with respect to T comma P, we can calculate. Yes, with respect to T comma P we can calculate. The further we can calculate U with respect to T comma P. So if there are any doubts regarding how to do it, then I will explain it later. Otherwise we will go forward. Do you understand this concept, like how to do it?
No doubts.
Okay, thank you.
Yes, sir.
Okay, fine. So yeah, if in the future if somebody asks that, okay, you know that, okay, we can't even simply sit and say that, okay, U is TDS minus PdV, give me the formulas for entropy and volume, I will calculate the internal energy. They will say that no, I have done the temperature and pressure, give me the values regarding this one, so temperature and volume. So then you can use this one. So now we will define, so basically now we will define the chemical potential system, which I saw in the third class. So now we will come more into systems. So now let us consider the Gibbs energy, dg equal to vdp minus sdt. So this is correct only, right? AGHU BSPT. So dj equal to minus s dt plus vdp. Yeah, so this is the equation written here. So now why we have taken this one equation was, so from this equation we can calculate anything. So because this is the basic equation with the temperature comma pressure, we can see that. So that's why we have taken this equation to define the chemical potential. So what I am doing was, if I apply the reciprocation rule, sorry, if I apply the reciprocation rule, we will get, say suppose this one as dg by dv dp at constant temperature equal to V. So that's what I have written here. So this one second, I will remove it. Yeah. So now what we will do was, so what I have done was, say suppose I at constant temperature, so I'm not changing any temperature, I'm changing only pressure. So I'm saying that okay, I want the second position from, say suppose I want to find out the temperature difference at the second position with respect to the constant temperature. If I put constant temperature, this will get 0. So now the equation is Tg equal to Vdp at constant temperature. So now what this will do was, so now if I want to say dg, if I do the integration, and so it will become as g2 equal to Vdp. So basically it is nothing but, so this is for the normal. So if I do for 1 molar, then I will apply this one to get the intensive properties. So then now I will get, so basically this is the Gibbs energy, right? So T at P2 minus, so this is minus, so what I am getting was, from where I am going to was, okay, so this is the basic equation. You need to point out second position, this is the one, and I am removing this all. So now we have this equation. So now if I take the ideal gas condition from this equation, if I take ideal gas, so it will become this equation where PV equal to RT, V equal to RT by P, RT by P. So now this one, so now what I am saying was, say suppose we have this equation T of P2 equal to T of P1 plus integration of P1 P2 RT by P dP. So which we will get, I will write one more equation, T of P1 plus ln of P2 by P1 into RT. RT is constant, so that's why I have taken as at constant. This is constant value and this is constant value, so that's why I didn't mention it here. So now you have this value. So suppose what will be the initial temperature? So we can't say, right? So okay, I have taken initial condition and then we move to some condition. So that's why we have taken the standard one as 1 bar. So that's why it will become, then it will become as G of T to P2 is equal to G of T at 1 bar. You should remember this, at 1 bar. So that's why we are writing G naught dot. So if you see the dot upside denotes the 1 bar at standard pressure. So that is what we have discussed as the initial point. As initial point, so plus RT ln of P2 by P1. So now here the P1 will be 1, so that's why it will be G naught of T plus ln of P2. It is nothing but ln of P. So that's what here. So why I'm mentioning it, was so no. So then we will go to this equation. So now, as we discussed, I showed it why we have taken this equation. So now we consider this as initial condition, standard temperature, pressure. That's why we got this one and this will be 1. But you should remember that logarithm has no units. That's why, so this has bar and this is also bar. So both will get cancelled. So it will become as dimensionless. You should remember this. We have some value at P1. That is the initial value. You need to remember that as standard pressure. So now this pressure, this Gibbs energy is converted to the chemical potential. So this is the formula which you are seeing in the, I think, third week class. So this is basically derived like this. So here what we are saying was, so what we written was g of t comma p p2 equal to g degree plus ln of p, right? So this is converted to mu equal to mu naught plus ln p. Okay, if you want the proof of this, say suppose why we are writing g dash as equal to ui, so gi equal to ui, it means if I say this is the second position, so then u2 equal to u naught plus ln p. So if you are asking me that how you can get from here to here, so then I will show you one example. Suppose we are taking the two component system. I think, yeah, this is the one actually. Suppose we have taken two component system. Two component means we have taken two systems with two systems which have n1 and n2 number of molecules, and the function is the Gibbs energy of whole system will be depend upon the comma lambda n2. Lambda is a scaling factor here, so it can be any constant value. So this will be nothing but, so we can write like this, because this is a scaling factor, we can bring it out. So now I applied the differentiation with respect to the lambda. So if I apply with the differentiation with lambda, so if we apply with the differentiation with lambda, we'll get this equation. And then what I'm doing was I'm applying the chain rule again inside it. Say suppose here we are keeping the temperature and pressure as certain values. So if you see, we have kept already the temperature as constant. We are not changing this value, so we are keeping this one. We are doing only with this respective, So then we are get dg by d lambda n1 into d lambda n1 divided by d lambda plus dg d lambda n2 d lambda n2 by d lambda, it is equal to, as it is will be d lambda g, so it will be cancelled. So the right side you will get only g. So we all know that from the initially we discussed that this will be the chemical potential of mu1. So it is basically nothing but lambda constant, because n1 is a constant value, lambda is a constant, so n1 will come out. So it is n1 plus, again this will be mu2 n2 equal to g. So what I am saying, it was sigma mu I ni equal to g, the total value, so which will gives rise to mu I equal to gi. So that's why we will convert this equation into this equation. So that's why we will write the chemical potential as mu naught plus ln p. Any doubts regarding this? Why we are writing mu? If you have seen the class, we are getting that mu naught, mu equal to, one second. Yeah. In the class, if you have seen, we will get mu equal to mu naught plus ln p, and then in the further classes you will see this ln p will go as fugacity value, and this will explain in the further classes. So we will write this value as this value. So you understand now, right, how the mu is, how we get from the Gibbs energy to this formula. Any doubt regarding
Yes,
this?
sir.
I will explain it again if you have doubts.
No, sir.
Okay, fine. So now in the third class we are talking about the open systems. So now here we have the two examples. One is the system where I showed it in the two different ways. So suppose the constant volume is nothing but, we have one system with constant volume, some mass is entering in, some mass is exiting out. So it means so what we need to was, so we need to understand some basic notations. One is mass flow rate, which is nothing but m naught, and molar flow rate, which is n naught, and then volumetric flow rate, we know that how much volume is passing through the particular area, and then velocity. So we know that density equal to mass by volume. So here we have the flow rate, so it will be density flow rate equal to mass flow rate divided by volumetric flow rate. So then mass flow rate equal to into density. So basically the density is nothing but volume into area, velocity into area, so it will be, yeah. So now we got this formula. So now we have the molar formula equal to this. So now what I have done was, so now we have from the laws of mass convert. So you know that from the laws of masses, so whatever going inside is coming out. So then accumulate here, the external mass is now won't be there. So it will be like m1 minus m internal minus m out will equal to delta mcv. The So then that's what if you use over finite time, suppose this is the one at one time, saying that whatever the velocity comes in, that will goes out. So that is the conserved mass. So whatever goes in, it will goes out. At steady flow means dmc by dt equal to 0, which says that sigma of n equal to sigma of out. So this is basically the mass flows. So for open systems, when the system is when the system is transferring the mass from one point, so one system to the surroundings. So this is how it is happening. So if you know this one, then we will go to the further slides. So suppose we have taken some complicated case where we have the system and some mass is going in, some mass is going in and some mass is coming out, and there is a heat generated and work carried out. Heat is transferred to the system and work is carried out from the system. So here we need to understand the constant volume. The changes in the constant volume will nothing but m in plus q minus m out plus m out. Please note this is out, not in. So now just note this as out, not in. This is out. There is a mistake. Yeah. So now you can see the change in CV. Basically the change in CV will be, see initially it will be the 100. Now if it is 125 means something came in, we changed the value of 100 to 125 and something goes out. Okay, so that's why we are saying the change in CV is equal to nothing but energy in minus energy out. So basically we know that energy equal to kinetic energy plus potential energy plus U. U consists of internal energy. So in the first class itself we discussed what is internal energy. It has the rotational translation of the molecule on all these things. So then if you see dE by dt, so this is nothing but change in the CV, equal to inlet kinetic energy potential energy plus U minus outlet kinetic energy plus potential energy plus U. So which we are applying for the molar flow rate. So we are applying the m into mn. So these are the two things. The Q work is carried onto the system, so that's why it is positive, and work is going out of the system. Is there any doubts in this? So if there are no doubts regarding this, so then comes the next one. We have the steady flow and steady state. It means there is nothing changes when this something is happening. So then it will be dE by dt equal to 0. So that will give us this equation. So basically this will go to this will become as q minus w equal to sigma out minus sigma n. Basically this will become as 0. So then we are taking this side and we will move this to this side. So then it will become like this. So that's what written here. I think down one will not be shown. So now I want to give some basics. Basics of what do you mean by kinetic energy, potential energy and internal energy. So if we come from kinetic energy says that when a force F, we have already studied the force in terms of kinetic energy in terms of work. Say suppose you apply the volume and then it moves dl length. So then we have PV into dl. So it gives us to area. Then we have PA dl. It gives rise to PdV. Okay. So this is regarding the work done. Now if you are taking the kinetic energy acting on the body, say suppose you are applying some force to the body. Such suppose you have the one object in your hand, you are applying some force, it is moving to certain distance with acceleration A, and say suppose the body has moved dl length. So then the work done will be dw equal to F into dl. So now dw equal to mass into acceleration into dl. So it is same thing as work done. There in the initially we have talked with the pressure. Now we are talking with the force. So that is the basic differences which we are focusing on. So it, acceleration nothing but dv by dt. So into here we have L. So now what we are doing was we are taking it as, so it is nothing but the distance by time. Distance by time is nothing but the velocity. So mv dv. So now work equal to this one, and then this is the kinetic energy work acting on the body, and comes the potential energy. You know that Potential energy is, suppose the body is flowing from one point to another point, point 2, so the height is z1, z2, and the gravitational force acting on it, so then it will be mg z2 minus z1, even if you go up also. So this is potential energy, and there will be kind of potential. Suppose if you are talking about the internal energy, suppose you have the molecule. So in the initial class I discussed, I think. So it has the coordinates. So after some time it will move its coordinates, or it can rotate along its axis, or it can vibrate along its axis. That's all called as potential energy. Sorry, internal energy. When we are considering about the energy carried out inside, we are considering the kinetic energy, potential energy plus internal energy acting inside minus outside. So this is the formula which we are writing. So whatever I have said it here is going like this. So we are taking the m out outside, the flow mass flow rate of u square from the kinetic energy. This is from the potential energy. This is from the internal energy. This is from the again kinetic energy. This is from the potential energy. Again this is from the internal energy. It is equal to q minus dw. So this is the basic formula which we have. Is there any doubts up to here? Delta u plus half into delta u square plus g into delta z equal to q minus w. Q is acting on the system, w is acting outside the system, so that's why it is negative. So any doubts up to here?
No, sir.
Okay. So now, so say suppose in the same case we are applying the pressure on both sides. So there is a pressure this side also. So now if you are applying pressure, so the work done will be in the two cases. One is shaft work, another one is exerted by the pressure. So pressure exerted by it, we already know that W equal to minus PdV. Sorry. Yeah. We already know this. We already know this formula. The shaft work is nothing but the mechanical work. I mean, as we have discussed previously, that the force acted on it without transferring any, without changing any input or output parameters. So that's what. So now the work will be this plus work carried out by the pressure, shaft work plus pressure. So that's what I have written it here. So it is total W. If you see this equation, just see this equation. So now we have this equation. Now I will remove all this. So basically, yeah, basically W total equal to W pressure plus W shaft work. So which gives to us delta U plus, so of U square plus GZ out minus in equal to Q minus WS plus, I can write it as delta V because we have the chain rule, W equal to PV, dV equal to PdV plus VdP. If you remember, we are only considering dW equal to PWV. We are not considering this in the state function, but if you are going for the path function, suppose if this is the path, pressure to temperature, you are taking this path, volume, or if you are taking this path, you need to consider the path which it is following. So then at that time you need to consider this one also. So then that's why change in the W equal to change in the delta PV. So then we have delta PV. So now the delta PV will be sent, it is in the negative form. So now we are sending. Okay, so this is internal energy. You need to remember this is big one. This is kinetic energy plus G into Z delta G. So it will be plus delta PV equal to Q into minus V. So we know that enthalpy equal to U plus PV. So it will be Q minus WH equal to delta H plus of delta U square plus G delta S. So this is the equation which we have it here. The work done for open system at steady state and steady flow. Steady state means steady flow means we have mass is equal to 0, and steady state means the conservation of energy is 0. Okay, so then we have this equation. Is there any doubts regarding this equation?
No, sir.
Yeah. So now, mm. so now we'll discuss this formula, which is shown in the example one. Uh, you can read the question, and I'll give 2 minutes time. We can discuss this one. So in the question given in this form was system is used for the various process in the bioprocess industry. Heating of liquids. Yeah, this they given the one. This is like a theory. So the thermodynamic properties of steam under various conditions, condensed, saturated, or superheated, are available in the steam tables. So yeah, so there is steam tables. If we have the James Smith book, maybe I will share of the class in after in the thermodynamics table. I will share you the steam tables. So basically, the steam table what they have done was at every temperature and pressure, they have taken temperature and pressure. They have calculated the enthalpy, sorry, internal energy, enthalpy, and entropy. So that's what they have done in the steam tables. So generated steam available at 100 kilopascal in a saturated condition is compressed to. So they are changing that. Initially they have the temperature as P1 and it is compressed to 300 Kelvin. The compressor designed to work in adiabatic process. So adiabatic means no heat transfer. No heat transfer. The compressor efficiency is defined as the, so they said the compressor efficiency is defined as the work isoentropic divided by actual work is equal to 0.8. Estimated work needed to operate, so they are asking estimate the work needed to, so they are asking to work to be considered. So if you take this formula, they are asking this value. And they said okay, so if you can understand the question, right, what they ask. So can you tell me what are the say suppose the formula is, we know the formula is delta H plus half into delta U square plus G into delta Z equal to Q minus WS. Okay, so now the WS means they given out minus in. So this is the first condition and this is the second condition. So it means to get the work done, you need to find out out minus in. It is nothing but, I mean, what I'm saying was this whole equation. Sorry, 1 second. Yeah, so now you need to find out Q minus S, where you say that delta H plus of delta U square plus G into delta J. So here they clearly says that didn't have any difference in. If you find out this one, they mention properly that we don't have differences in the entry and exit levels. So entry and exit elevations. So from here they didn't say there no difference. It means delta Z equal to 0, and they said work in the adiabatic process. So it means no heat transfer. It means Q equal to 0. What about the kinetic energy, the compressor? I think in the original question, if you see, so in the original question, as the sir explained, the values are potential energy is 0, which I said it from here, and the compressor is 0. They say I think sorry, yeah, and equalized exit and entry values. If you see this one, we have equalized values, equalized entry and exit velocities, which says that okay, which says that delta U equal to 0. From this we got this one. The initial condition is saturated and it is superheated, because they that also they mentioned. So now we need to find out the values of enthalpy. So basically they didn't ask the enthalpy values, they asked the work. So there are two questions here. One is estimate the work needed, and the second one is enthalpy. So have you seen the steam table? How does it look like?
Yes, sir, but I don't know how to use steam table.
Yeah, I will explain you. Say suppose there is a T, P, and there is internal energy. I think this is the format, right, which they have it. So this is values at 100 Kelvin. Example I am giving. This is that 30 kilopascal, and there is one value. Say suppose 5. Example I am giving 10, 20. So this is how it looks like, right? Saturated and superheated. So this is for the saturated steam table, and there is superheated steam table. Have you seen these two tables, steam table in these two formats? I think appendix
Yes,
C.
sir.
Yeah. So now you need to understand two things. So now, uh, yeah. So they said in a saturated condition. So you need to go to the saturated steam table, and you can look at the P values. So go until P as 100 kilopascal. Do you have the steam table with you? You can try it out. If you have it, you can try it now itself.
Yes, sir, I'll check.
Okay. So I think you won't have exactly at 100 kilopascal. You will have maybe around 98.4 or 100.6 like this in the saturated steam.
There is 101.33 kilopascals.
Sir, come again. One not?
1.33.
No, no. You should 1.33 or 103.3. What you're saying? I'm not getting. Uh, if you go till down, you will get the values. There is a big table, right? Super saturated system with the T and P. Check the P values from it will go from I think 0 to there is some value at where you will get at 100 or 70, 98, 120 or 110. Are you able to get it? Hello.
Sir, there is 101.33 kilopascal.
Okay, 101.33 kilopascal. Fine. What is the upper
Yes,
one
sir.
before this? What is the value we have? Like you have the 101, right? What is the before this one? Which value? Pressure?
97.76, sir.
97.76 kilopascal. Okay, fine. So can you tell me the entropy value, sorry, enthalpy values, H values for this? If you go through the same line, you will find the enthalpy for the both the cases.
Sir, for enthalpy, there are three values
You need
like
to take the last value.
saturated liquid.
It is saturated vapor, right? So if you see that there is, if in the question they have done the generated steam, steam is nothing but the vapor. So it is the saturated vapor. You need to check under the saturated vapor.
Okay, sir.
Yeah.
Sir, it's 2674.74.
One second. One second. One second. For what? 97.76 or 101.33? Which value you are telling? For 97.76, how much is the enthalpy?
2674.4, sir.
Point 4. What about 101.33 kilopascal for this?
2676.0.
Okay, so these are the two values, right? You can see the screen now. I think so. The values
Yes, teacher.
is it correct? The values which I have written 2674.4 27.
Sir, for 101, it is 2676.
Okay, fine. Now I'll tell you how to calculate the entropy at the exact position. So basically, it is basic normal mathematics. Say suppose you need to write it as a 3 points. So x1, x2, x. So basically, what I will do was x1, x, x2. So basically, this is before point. This is the needed one, and this is the 101.33 Kelvin. So here the enthalpy is 2674.4. Here you don't know. Here it will be 2676.0. So what I will do was, uh, one second, I will make it in the new slide. So what are the values we have? Okay, we have 96.76. So we have 96.76. The values are 2674.4. We have 101.33. We have so 2676. So yeah. So now how you will calculate was, take it as x1, x, x2.
Sir, it's 97.76.
Okay, sorry, 97.76. Okay, so now take it as this one. So the pressures and the enthalpies you have. So the pressure one is 97.76. You need to find out at the 100 kilopascal, and the new value is 101.33. The enthalpies are 2674.4. This value you don't know. It will be 2676. So the desired value will be x2 minus x divided by, so this is the formula. So basically we are doing the, how to say it. So this is the formula how to calculate. So you have the x2 value, okay, and you have the x value, and you have the x2 minus. So the basically x2 is the x are the pressures, m is nothing but the enthalpies. So basically what you are doing was, if you take the graph of pressure and enthalpy, we have 2 points. Say this is the pressure 97.76. Here you have the point of 101.33, and here the pressure is something around say 2674.4. Here it is 2676, and I am making two dots, here one and here one, and I am mixing these two, and say suppose, and I want to point this one. So you need to find out this one. So now you need to find out the line equation. So line equation is y equal to mx plus c. So in the same way you can do it. So from here you will get this formula. So basically you can remember like this. If you have two values, just take x2 minus x m2 plus x minus x1 plus x2 minus x2. Because see, this value is increasing, so that's why we are taking x2 minus x. Here this will be decreasing, so we are taking x minus x1. So I think this formula is already given in the steam table in the first page. If you have taken the, is it appendix E or which appendix it is? I think it will be in the appendix E or H, not sure. I will share this steam table again, which I have it in the drive link which I am sharing. Hello.
Yes, sir.
Yeah, from this formula you can calculate the enthalpy at 100 kilopascal, and the same thing you can do it for 300 kilopascal also at superheated values. So there are two different steam tables. One is for saturated, another one is for superheated. So from this you will get the 100 kilopascal using this formula. For saturated also you need to look into the table. You will get x1, x2, m1, m2. You have two different points and you need to find, you have this point, so then you need to find out the y. Okay, the slope of this line is x2 minus x1 by, sorry, y2 minus y1 by x2 minus x1. So that's the equation we have it here. So you can calculate like this. So basically the formula is, sorry, m equal to x2 minus x2 minus x1 divided plus x minus x2 minus x1. So you understand, right, what is x2, what is x1 and x2?
Yes, sir.
So I will recheck it and I will share you the files. I think by tomorrow morning you will get these files, right? So in this file you can once look at it again in the steam table itself. On the first page itself there is a formula how to calculate it. So from that formula you can recheck it whether the variables which I am using are right or wrong. But the method is same, okay? So in this way you will calculate the enthalpies. Okay, so once you calculate the enthalpy, so you will get the enthalpies here. So you will get the values of enthalpy. Once you get the values of enthalpy, you know that work is nothing but delta H. So delta H at 300 minus delta H at 100 kilopascal. So yeah, this is the one value which you will get, and you know that as given divided by work. So they said that so this is the isoentropic work which you will get. So you will get the work done is this one, and they are asking for the so the value they given is 0.8. So you are calculating the isoentropic wall, so you know this value, and they are asking to find the y. So y equal to x divided by 0.8. So this is how you can do this formula. So any doubts in this one?
No, sir.
Okay, if you have any doubts in week 1 and week 2 you can ask, otherwise I will explain the new cons. 1 second, sorry. One second, new slide. If you have any doubts regarding the first week and second week assignment, you can ask me. I'll explain that. Otherwise, we can go for the PV equal to RT cases.
Sir, I have a doubt in week 1 assignments.
Okay, tell me what is the question. If you remember the question, I don't have the question now.
Sir, it is related to PT diagrams.
Okay, explain me what is the okay, the critical point 1.
Yes, sir.
Okay, so what is the okay, I don't remember. You can raise the question in the what do you call discussion form. I will explain. So what is the question? They say they are saying from critical point. They given the 4 options, right? We need to go from one point to another point, and what does it call as?
Yes, sir. Yes, sir.
Okay, so what is the mistake you have done? I mean, what is the doubt you have in this?
Sir, I don't know how the answer is the correct option. I gave the TC and PC are critical point, but the answer is the fourth option or third option.
Okay, I'll look into this and I will discuss with you. Okay, later I'll explain you this one. I thought
Okay, sir.
I thought the questions are easy ones, so I thought that's why I don't have any doubt. So I thought I have made the questions for the formulas, but I didn't see that question. Okay, I'll let you explain in the next class.
Okay.
Okay, if there is any wrong thing, I will mail to the professor also. If there is any,
Okay.
okay, okay. If you have any questions regarding the problems, you can ask me. Do you have any doubt regarding the problems in the second assignment? So I have answers for the second assignment. So for the second assignment, second problem, you will calculate through alpha by k. And the sixth one, you know that du equal to cv dt. If you don't have any doubts, then we will go through. We have time, so I will explain you the basics of the phase rule. Once we have the phase rule, so we have the ideal gas. So we are going for the virial equation and cubic equations. Hello.
Yes, sir.
Yeah. So we have the equations PV equal to RT. So we know this is the basic ideal gas equation, right? So under different conditions, how does this equation changes? That's what we are going to see today. Under different conditions. So different conditions in the sense isothermal, isobaric, and adiabatic. And then we will go how to do it for the real gases. So we know that PV equal to RT. So we have we also know that du equal to cv dt, du equal to cp dt, dh equal to cp dt, sorry. And so it means h of t equal to cp of t. So here we have u of t equal to cv of t. So you know these 2 points, right? So which are dh equal to dq, dh by dt equal to dq by dt. Change in the heat with respect to the temperature is nothing but C. So that's why we have written dH equal to Cp dt. And the same thing with the volume. So du by dt is equal to Cv. So it will give rise to Cv dt. So these are the two equations which we will go through the further. I think I need to make one slide. So 1 second. New slide. New slide. Yes. So what we have the basics. Du equal to Cv dt, dH equal to Cp dt. So once we have this equation, we know that H equal to U plus PV. For the ideal gas, we know that PV equal to RT. So this will go as H equal to U plus RT. So if we consider in the function of time or temperature, so it is nothing but Cp Cv plus RT. So now, sorry, Cp of T temperature. So now if I apply the dCp by dt, no, 1 second, I made a mistake, sorry. So we have this equation. So now dH equal to, sorry, H equal to U plus PV, H equal to U plus RT. Now dH with respect to the dt equal, sorry, yeah, dH equal to du plus r dt plus tdr. This is constant, so it will be 0. Now if I apply the with respect to the temperature, it will be like this. So this will be Cp equal to Cv plus R. So from here we got Cp minus Cv equal to R, one of the important equation. equation 1. So now if I go through, so now if I take the equation of du equal to cv dt, so now you know that u equal to q plus w, so this will be goes like d of q plus w equal to cv dt, and then dq equal to cv dt minus dw. So we know that dw is nothing but pdv, so the work which is minus pdv, so cv dt plus pdv. So now, so we know work equal to minus pdv, and sorry, dw equal to dq equal to cv dt plus pdv. So now converting the equation entirely into the pv equal to rt, so v equal to rt by p, and if I convert v equal to rt by p, if I do dvt with respect to the temperature pressure, I am changing it here, so it will become as drt by dp. It is nothing but it will become as, now the q will be cp dt minus rt dp by p, dw equals to, the dw equal to minus r dt plus rd dp by p. You can try this one, how you are getting from, say suppose we have pv equal to rt, v equal to rt by p. Now I want to do it with the dv, because here we have the dv, right? So now we need to convert this dv to this equation. So now we have here two things, so rt on the upper side and the p on the downside. So if you know the u by v rule, so it will be v square uv dash minus vu dash. So you can apply this rule, v by u, it is equal to u square vu dash minus uv dash. If you apply this rule for d of rtb pi, we got p square vud dash, so it means rt into dp of p minus, you will get p of r dt. So now if I take r by p common, here it will get 1, so it will be dt minus t, here we get t t t t, so minus t dp by t. So for this it is dq. So now the whole dq will be cp dt plus minus rt dp by p, and dw equal to minus r dt on dp by p. So these are the two equations with respect to the pressure change. Why we have taken the pressure change was to apply the term, sorry, see suppose initially we have q and w in terms of volume, because p dv and all the things. Now we converted this into temperature and pressure, so that we can understand the problems of isothermal and isobaric. If I consider the two systems, if it is isothermal, this will get 0. If it is isobaric, this will not happen, and we will have only cpdt. The same case for the q also. So basically this is the basic equation for the ideal gas. If you have the pv equal to rt, how the isothermal is changing, how isobaric is changing, and how the adiabatic is changing. Adiabatic means there won't be any heat transfer, so that time it will be, this value will be 0. Then you will get cp dt equal to rt dp by p, then you will do dt by dt equal to, you can write it as r by cp dp by p. So then you will apply the integration, then you will get the with respect to t comma p. So this is for the ideal gases. So now, okay, if I take ideal gas, This all equations will be valid. What about the equations for the real gases? So there, so you understand, right, what I said till now? So what we have done was, hello,
Yes, sir.
the concept is clear, right? This concept, the PV equal, sorry, the PV equal to RT, and how the CP minus CV equal to R came, and from here we calculated du equal to CV dt. From here we get u equal to q plus w, we put it here, and then we obtained dq dw in terms of temperature and pressure by changing v equal to RT by V T. By using the differentiation formula you get, you understand this concept, right? So how the isothermal it is changing, isobaric it is changing, adiabatic it is changing. I think it is in the week 1
Yes,
slide, I
sir.
think, if I'm not wrong. So now, so basically if I take ideal gases, ideal gas it says that it is a large volume, volume is large, and the pressure will be less. So the molecules will be so far away, sorry, it, here the length will be more such that there won't be any attraction or repulsion forces. But if you are talking about the ideal gases, the pressure exerted will be more and the volume will be reduced. It means the molecules are coming closer. So that's why the PV is not equal to RT. So that's why we need to come with the new equation. So then the virial equation came, which says PV equal to compressive factor by RT. So basically the compressed factor says that initially they said that it is nothing but V real by V ideal. So if you take the ratio of V real volume of the molar volume of the real gas divided by molar volume of ideal gas, you will get PV equal to RT. If it is for the ideal gas, it will be 1. So then it has follows the PV equal to RT condition. If it not, then we need to get the PV equal to Z into RT. Suppose then if the terms of attraction came, attraction or repulsion between the two molecules came, so then what they have done was they use the same formula, PV equal to ZRT. So that is only for if we have only real gas and ideal gas. But say suppose there is attraction and repulsion happening between two pairs or three pairs. So then they expanded it in the Taylor series. So to get Z equal to 1 plus beta of T plus V plus C of T plus V square plus D of T plus V cube plus and so on. So as if the value is so close, we are removing these terms basically. We are keeping this 0 because the low here the volume will be very low. So now the Z will be in the terms of 1 by, I think it will be C2 or I don't know the notation. So it will be V. So suppose if I use it as C1 and C2, it will be V square. So here in this we are considering the attraction between two atoms because it is second term. If it is the third term, we are considering the attraction between three atoms. So what they have done was, so until now also they didn't know how to calculate the attraction and repulsion forces. So that's why they have expanded the what do you call this factor in terms of Taylor series, and they got, okay, this will be the reaction of beta plus V plus C of T by V square, and so on. As the V volume inversely volume is increasing, it will tends to 0. So that's why they have taken these three terms, 1 divided by B of T plus V plus C of T plus V square. So if I plot with the T with function, so with pressure, at some point this will at time T equal to 0. So that's why we will get B of T. So basically this is B of T. So if I carry out the experiment for the B of T with respect to the temperature, the curve will go like this. At some point of T, at some point of temperature, we will get the 0. So there we need to find out that value. The same thing for the T square. So once they found out this, then comes the cubic equation. So cubic equation was basically designed for, say suppose, how to say it, we already discussed that PV equal to RT. So what they did was, so initially they consider that, I'm explaining the van der Waals again for the better understanding. We have the two molecules. So just consider the only two molecules or three molecules. As the volume is lesser, there will be more occupants of each molecule in the system. So suppose if I take this one, if this is the total volume and if this is the total volume of without anything, so this volume is V, and say suppose the volume occupied by this molecule will be B. This one is B. So that's what they have done was, they have removed the molecule weight, and then I think I need to add one more slide. This will be the last slide, I think. So yeah, so they said PV minus VB equal to RT, and then they understood that okay, if two molecules are, if the volume is very less and we are considering the two molecules, what about the, so P is here is P external, you need to understand this. So this is the P external. What about the pressure exerted by the single molecule while while going towards the wall or between the two molecules? What will be the attraction force and repulsion forces? There will be some pressure exerted by this. So they said that pressure will be. So what is the equation? I forgot. One second. So now, say suppose there are two molecules in the low confined space, which will be in the 1 by v square. So where we will get the attraction force between these two. So they mention it as A. So that's why they called as P plus A by v square. It is equal to V minus B. So this is the volumetric equal to R by, so P plus A by v square equal to RT by V minus B. RT by V minus B minus A by V square, it is equal to pressure. So if we consider PV equal to RT, ZRT, if we have the Taylor expansion, Z equal to 1 plus beta B plus C by V square and plus and so on. C by V square they have added it here, and 1 by V they added it here. So this way this modification of this equation is this one. So what here they done was, so they didn't consider any effect of temperature. So to bring the temperature effect into the system, I think they are given the values. Sorry. We have the so for this equation, so while doing many experiments, they found out that A equal to 27 R square critical temperature point 64 PC, comma B equal to RTC 8 PC. Here in this case, in the van der Waals equation, they didn't consider any effect of temperature. So to bring the temperature effect, to bring the temperature effect, the Redlich, I think Redlich Kwong EOS has made the new equation. It is simply the updated version of van der Waals equation. RT by V, it will be Vm minus B minus A by T to the power of 0.5 Vm by Vm plus B. So he wants to consider the, so this is the equation. So the virial equations and the cubic equations. So if we consider the initially, so the virial equation is nothing but PV equal to ZRT. The cubic equation is where we have considered the effect of the attraction and repulsion, all the properties. So that's why the difference is. And from this formula you can estimate the volume. Okay, these are the, I think this is the classes which has happened in the third week. So until now, in the first week, the second week, you have any doubts regarding this? Hello, uh, hello. I think the call got disconnected again. Yeah. So basically, okay, I think it's not disconnected. So basically, as of till now, in the last 3 weeks, we have discussed. If I put it in the good words, in the in the last 3 weeks, we have discussed the starts from how does the internal energy changes, what is the thermodynamic system, and how does the system changes. In the second week, we have discussed that okay, how can we represent any given system. Say suppose if I say that I have temperature and pressure, how can we change it? That all we discussed with for the closed system only, and then we introduce the term called as chemical potential. Once there is a chemical potential, and then we have the topic of okay, I have the chemical potential and I have done these things. How can I make sure what do you call, the system has been okay, I have the system with a closed system which says that u equal to tds minus pdv, and I have done the all the system. So in the closed system, it doesn't mean what do you mean by closed system was there won't be any heat transfer, energy transfer between the two systems from the outside. If I take the example of closed system, will be ice water in the bottle, so the mass won't be transfer between the outer system to the surroundings and surroundings to the system. So, and that is explained, and then we have the open systems, and we have checked the how the masses is and the energy flow is distributed or conserved between the open systems. And then I have shown the chemical potential. So once we have the chemical potential, I think we have already carried out the experiments, and then we have the virial equation and cubic equation, and we have discussed about the steams. So if you have any doubts, you can discuss. Otherwise, we will go to another new topic. If you want me to explain, I will explain some interesting topic which I learned regarding the chemical potential. So basically, if I am talking about the chemical, hello,
Yes, sir.
yeah. So this is the topic up to third week. You have any doubts regarding the topics up to third week? I think
No, sir.
third week assignment is also easy one. I mean, you can calculate the formulas using the isoentropic, the equation, and the following up. If you have the isoentropic equation and you know how to, if I give any equation, sorry, one second. Yeah, if I give, say suppose if I give any equation to ask in the terms of if I give, say the temperature is raised from this point to this point, and pressure is raised from this point to this point, or this point to this point, and h of t comma p we can calculate using Maxwell relation with respect to the Jacobian, using the mnemonic diagram also. So then we have find out that g is plus RT ln P is nothing but mu equal to mu naught plus RT ln P. So can you tell me, basically this equation is nothing but chemical equilibrium. You have any idea why we are using the chemical equilibrium? Hello. So can you explain me what do you mean by chemical? Do you know anything about chemical equilibrium? If you guys, so I will give one example, then we will wind up the class. I have the system where I put, sorry, where I put the one second, where I put the one skin of our molecules, where what will happen to the skin if I put at the, say, in water bath. What will happen is the skin will succumb all the water, it wants to succumb all the water into it until it become big and it will get burst out. Otherwise we can take another example. Say suppose I have water and I keep one ice cube. So why the ice cube get melted? Otherwise if I take another example of into ammonia plus the ammonia synthesis, if I take ammonia synthesis, one second, yeah, if I take ammonia synthesis of into N2 plus 3/2H2 will give rise to NH3. So how the mixing is happening? So this is pure, and this is mix. So so for these terms we have the chemical potential. The chemical potential is basically G of T comma P, sorry, G equal to N1 N2 components. When you have this components T comma P, so suppose I have taken I have kept the system at constant temperature and pressure and I kept both. So now there will be exchange between these two, so then only we will get the chemical equilibrium, right? Until what time the chemical equilibrium will be attained? So chemical equilibrium is nothing but, say suppose if I give this example, there is system of mixture of A plus B and there is one boundary and there is A. So if I kept it at the constant temperature and pressure, so then what are the parameters which will affect the system? So this will move this side and only A can move it, and this will move this side. A of, one second, so A from here will move to this direction, A from here will move to this direction until it attains chemical equilibrium. So this is one nice concept where you can say mu of mixture will always be less than the mu of pure. So that's why whenever you see the solid gets to liquefy, so the solid mu value will be higher than this one, so that's why mu chemical potential wants to decrease it. So from here only you will get the, say suppose if you have any reaction, we will talk about the equilibrium constants, right? So all the equilibrium constant will arise from this point delta G. So yeah, if you have any doubts regarding any classes, we will discuss. I think I need to take another 10 to 15 minutes if possible class, because of the first half an hour is left, right? If you have any doubts regarding any topic, you can ask in the thermodynamics. So hello. I think we have done with the concepts, and for the thermodynamic classes, I think if you want to explain it in a much better way, you need to, it's better to keep all the ways correctly. Say suppose whenever you are writing the exam, it's better to make the mnemonic diagram and find out that okay, I have this scale AGHS, and you can from that, if you have the reciprocation formulas, use the reciprocation formulas and then you can do it. So that will be the better way. And yeah, I think this will be the up to classes, and if you have any doubts regarding the homogeneous system or heterogeneous system, we will discuss. So how can the homogeneous system is done and the heterogeneous system is done. You have any doubts? Otherwise, we will wind up the class.
No doubts.
Okay, thank you. Thank you for attending the class.
Thank you, sir.